Good afternoon, everyone. Hello there. Welcome to the Academy's Morrison Planetarium and this presentation of our final show of the day, a tour of the universe. Now, this is a little bit different from the other shows that we've been showing today. How many of you have seen our other show earlier today? A couple of you. Okay. This show is very different. That show, Living Worlds, is pre-recorded, pre-rendered. This show is entirely live, and what it involves is a flight through a 3D-dimensional model of the universe. So I'll be piloting us and telling you a little bit about what we see along the way. And what we're doing is we're using a piece of software supported by NASA that is actually a free download. So if you're interested in what you see on the dome today, you can come and see me up at the booth after the show, and I'll tell you how you can get this software. Maybe you can try putting it on your computer and trying the same sort of thing. Now, this is a live presentation since it does involve live flight through this three-dimensional model. I'll try not to fly too wildly, not crash into any planets or fly into a black hole. What you should remember, however, is that if you should find yourself feeling a little motion sensitive because of the movement, I'll try to avoid doing anything too crazy. Just close your eyes for a minute or so, and that usually helps. Now, during the presentation, we'd appreciate it very much if you could please refrain from eating, drinking, snacking, or any kind of photography or recording. This would be a great time to silence your personal electronics and put away or turn off any light-emitting devices like cell phones, tablets, etc. So, with that, one thing that I do have to add, we are going to try to end the show by 5 o'clock, which is closing time for the museum. And at the end, please just exit out through the doors at the top of either stairway. So, let's go into outer space. And we can do that by transporting everybody here in the planetarium, or virtually, to a point high overhead. And so, let's change the lights, turn on our dome image, and here we are, about 100 meters above the Academy of Sciences. So this is where we are in Golden Gate Park. I'm going to raise us up to about 100 times this distance. So we're about 100 meters. Well, actually, we'll go a little bit higher than that. We'll go up to about 100 kilometers, because that's the official definition of outer space, according to many international agencies. 100 kilometers, or about 62 miles up, is where aerodynamic control surfaces no longer work. Things like wings, flaps, rudders, and you have to use maneuvering rockets. So 100 kilometers is the edge of space, officially. But we're going to go a little bit higher than that, about four times higher than that, to roughly 400 kilometers, which is the altitude of the International Space Station. So this is the kind of view that the astronauts on board the station have of our planet from 400 kilometers up, roughly 250 miles. And that's as far as people go from the Earth right now. People have traveled farther from Earth, meaning we're going to continue zooming out away from where we started from. And we're going to go as far as humans have ever traveled, at least for now. And that would be our own satellite, the moon. Because roughly 50 years ago, between 1969 and 1972, people did travel to the moon, to our own satellite. So let's zero in on our satellite, which is a very tiny object right now compared to Earth. We'll move in there, 250,000 miles from Earth. So about 1,000 times farther than the International Space Station. And here's our satellite, the moon, our natural neighbor, 250,000 miles away. Now, it took those Apollo astronauts about 3 days to get here, but it takes something else a lot less time to reach the moon. That something else is light, or radio waves. They both travel at the same speed, 186,000 miles per second. And to get from the Earth to the moon at the speed of light would take only about 1.5 seconds, which is a lot faster than 3 days. And that's one way that astronomers like to measure distances in outer space, by comparing it to the speed of light. So when we talk about traveling as fast as light, which is 186,000 miles per second, we're talking about being able to travel from Earth to the moon in 1.5 seconds. And if we tilt upward and zoom away from our planet, we'll see the rest of our solar system start to come into view. Our own star, the sun, will come up from the bottom. And that is the center of our solar system, 93 million miles away, which takes light about 8.5 minutes to travel. And then away from the sun, we have other planets, of course. The nearest planet to the sun is Mercury. And then there's Venus. We on Earth, the third planet, 93 million miles away. Fourth comes Mars. And as we travel even farther out, we come to a big gap between Mars and the next planet out. That gap is filled with all kinds of chunks of rubble and debris left over from the formation of the solar system about 4.5 billion years ago. And those are the asteroids. Now, we're showing you a lot of asteroids right now, but there are a lot more. There may be as many as 1 million asteroids out there, according to some researchers, within a certain size range. But there are lots and lots and lots of them. Several 100,000 right here in the main belt between Mars and the next planet out, which is Jupiter. And then after Jupiter come the other giant planets, Saturn, Uranus, and Neptune. And those are the 8 planets of our solar system. But that's not all there is in the solar system. There are other things too. In particular, there's another belt of debris farther out in space, and that is called the Kuiper Belt, or sometimes also called the trans-Neptunian objects. And it's a mess. Look at all this stuff out here. And there are some that are in big, wide orbits that fly out, and they travel far from the sun, much farther than any of the planets. There's just so much stuff out here. And this is one reason why Pluto, which we used to be taught was a planet, was sort of reclassified as another kind of object, because it's in this Kuiper belt. And the definition of a planet is that it's supposed to clear its orbit of other stuff, and Pluto hasn't done that. But one more thing that I want to show you. We talked about how far humans have traveled. We've traveled to the space station, 250 miles up. We've traveled to the moon, 1,000 times farther than that, 250,000 miles away. And now we're going to see as far as any human spacecraft has traveled. Now, there are no humans on board, but these are our space probes, starting with Pioneer 10, which is the one going off by itself down to the lower right. And then that was launched back in 1973. And then the others going in the other direction are Pioneer 11, Voyager 1, Voyager 2, and the really short path there is New Horizons, the spacecraft that flew by Pluto. And those are the farthest spacecraft from Earth. They're the only ones that have left the solar system. The most distant one, Voyager 1, is about 21 light hours away, or roughly 17 billion miles from Earth. So that's a distance that takes light 17 hours to traverse. So even our most distant spacecraft has not traveled as far as light can travel in one day. It'll take a little while longer for it to get that far out. But now let's travel farther out from the sun, and we'll see the other stars. Now we're flying among the stars, and as we do, we'll see ourselves passing them in space, and the sky no longer looks like a flat surface. We're flying through the stars. And one other thing that I want to show you as we continue traveling farther and farther out, now we're crossing light years, trillions of miles of space, which takes years for light to travel. And one other thing I want to show you is something called the radiosphere. This is the most distant artifact of human civilization as far as our radio signals have traveled. Out here, about 90 light years from Earth. We've been broadcasting radio signals into space for about 90 years or so. So 90 light years in one direction, 90 light years in the other direction. So the sphere itself is about 180 light years across. And that's as far as any evidence of humanity's existence has traveled into space. And of course, you can see as we rotate around, there are lots of stars outside of that. Our radio signals have not reached most of the other stars in space. There are some inside, but not too many. Anybody living there on a planet orbiting any of those planets, or orbiting those stars, if they're inside the radiosphere, they may have picked up our radio signals. If they're outside, they haven't heard us yet. They wouldn't even know we're here. So we'll keep the radiosphere on as we travel even farther out into the galaxy. And we are traveling into the Milky Way galaxy right now. We're still within the Milky Way. About 100 years ago, astronomers thought that the Milky Way was the only galaxy in the entire universe. But in about 1921, an astronomer named Edwin Hubble showed that there are other galaxies out there. We knew how big our galaxy was, but then they found that there are other objects farther outside the confines of our galaxy. There are other galaxies. Not only that, Hubble found that the galaxies are moving away from each other. So not only did he discover that the galaxy, the universe is bigger than we thought, consists of more than just one galaxy, but he also told us that the universe is getting even bigger still because the galaxies are moving farther away from each other. Well, this is our own galaxy, the Milky Way, a huge flat disk of several 100 billion stars that measures roughly 100,000 light years across. And I say it's a disk because it is flat. If you go out on a nice clear evening away from city lights, you can see the Milky Way as a faint band of light crossing the sky. And that's what we see when we look along the plane of this disk. We see that band of light across the sky. But if we look in other directions, we're looking through parts of the galaxy that aren't quite as dense or thick. But it is 100,000 light years across, 100,000 years for the light of stars at one end of the galaxy to cross all the way over to the other. That's how big our galaxy is. But it's not the biggest galaxy. Of course, it's not the only galaxy. The Milky Way is one member of a group of galaxies called the Local Group. It's a collection of about 80 galaxies, which includes another big spiral known as the Andromeda Galaxy, another one called the Triangulum Galaxy, but about 80 galaxies clustered together. And there are other galaxy clusters farther beyond. Every spot you see on the dome here is no longer a star, but rather an entire galaxy. And this is based on actual data. These are the results of many, many surveys taken of the sky that show where the galaxies are located. So this is all the real thing, the real stuff. As we travel farther and farther out, we start to see the beginnings of structure in the universe. The way the galaxies are distributed has a very, very interesting texture. There are clumps of galaxies, great clusters and superclusters of thousands of galaxies separated by voids where there's practically nothing. And if we travel even farther out, we see what starts to look like a shape. And we'll see if we can get out far enough to see it. The colors that you see there in the galaxies, though, are not the real colors of the galaxies themselves. Those are just indicators of which survey was used to make this part of the map and populate that part of the model. So here we're traveling farther out from the galaxy. Now we are quite a ways out, almost 10 billion light years out. And the galaxy seems to have the universe seems to have a rather unusual shape, doesn't it? Looks kind of like a big butterfly or an hourglass with a very narrow waist and two big fan-shaped sections fanning out from each other. Is that the real shape of the universe? Well, no, it's not. Our model of the universe, our map, looks like this only because there is something in our way blocking our view of the part of the universe that's along the plane of our galaxy. All the dust and gas in the plane of our galaxy is preventing us from seeing these areas here, which we know there are more galaxies farther beyond. So as our instrumentation gets better, as our techniques get better, eventually we'll see this map fill out a little bit more uniformly so that we have an even number of galaxies all the way around. But right now, this is what we can see. And it's not the real shape of the universe, but it's just the result of the fact that we haven't mapped certain areas very well yet. And as we travel even farther out, we come to some of the most distant objects ever observed. And of course, you can see in this map how there are some areas in the universe, some parts of the sky that have been mapped out more thoroughly than others and explored more carefully. That's why there are some areas that are denser streaks, as you can see. And now these orange spots that we see are what are called the quasars. These are the most distant objects that have been observed. These are the centers of very, very young galaxies, and they're very energetic, so energetic that for their distances, they are the most energetic things that we can think of. They're very, very bright, very powerful, give off a lot of radiation and energy. And those are the most distant things that astronomers have observed. These are more than 10 billion light years away. And farther out, well, is there a farther out? Surrounding everything, permeating the entire universe, there is a faint microwave radiation, a faint background hiss coming from all directions that some astronomers think is the best evidence for what they call the Big Bang, the time 13.8 billion years ago when the galaxies began to separate away from each other. This was discovered in about 1968, was predicted in the 1940s. And when this radiation was found, as predicted, astronomers held it up as the best evidence for what they call the Big Bang. So this faint radiation is really a heat map of the universe. It shows some areas that are a little hotter than others, some areas a little bit cooler, and this shows the beginnings of the differentiation of matter, which means the formation of stars and galaxies. And this is as far out as we can see, as far back in time as we're looking, because the farther out into space we look, the farther back in time we are seeing, because it takes light time to cross great distances. The quasars that we are passing through, the light took 10 billion years to reach our telescopes here on Earth. Closer galaxies, well, their light took a little less time. And as we move back in toward the center of our model, it may occur to you that it seems as if we're at the center of the universe. Is that really the case? I know a lot of people would like to think they are. But no, we're not the center of the universe. The reason it looks like we're at the center is simply it's because we're the ones who made the map. It's a result of perspective. It's like being in a forest and looking around and seeing trees in every direction, and you just assume that you're at the very center. If there were somebody in some other part of the galaxy or some other part of the universe making their own map of the universe, it would probably look the same from their perspective as well. We're fast approaching our own local group again. We'll come back to our own Milky Way galaxy. We see it approaching us edge on. And as we approach the galaxy, we can still see the radiosphere there, telling us our location in the galaxy. We're not at the center of the universe, not even the center of the galaxy, but about 2/3 of the way out. And the radiosphere, our radio footprint in the universe, shows where we are. And with respect to the other stars that we can see, a lot of people ask, well, we've seen all these galaxies and all these stars. Are there other planets, other planetary systems like our own out there? And the answer to that is a very definite yes. Since 1994, astronomers have discovered lots of planets orbiting distant stars, many of them, as you can see, outside the radiosphere. But to date, the number of extrasolar planets, as they're called, the number of exoplanets is more than 5,000. So there are more than 5,000 planets out there, and counting. The number keeps going up because we keep discovering more and more. And of all those planets, are there any that are anything at all like Earth itself? Well, we just don't know because they're so far away. We don't know very much about them. In some cases, we can calculate their masses or their sizes, how fast they orbit their planets. We're beginning to get an idea of what their atmospheres might look like. Hopefully, with the new James Webb Space Telescope, we'll be able to figure out what those atmospheres are made of. But as we approach our own star, the sun, we're left with the realization that as far as we can tell, there are no other planets out there that we know of that are anything at all like Earth, that have the conditions required to allow life to exist. Now, for that to happen here on Earth, well, the planet has to be the right kind of planet, and we think it should be a rocky planet. It should orbit the right kind of star, which gives off just the right range of radiation so that it's not too dangerous or too hazardous to live under. It has to be the right distance from its star so that it's neither too hot nor too cold, and that liquid water can exist on its surface, something called the habitable zone. And it has to have a lot of other stuff too. It's got to have the right kind of mineral content and other nutrients that will allow life to exist and survive on its surface. And so far as we know, there's no other planet that has those conditions like Earth does. So our planet is unique in the solar system, or in the galaxy, in the universe, to our knowledge. It is the only one that does harbor life. Very precious, a very fragile place, one where life exists in a delicate balance with its environment, and one which we need to do a lot better to protect so that it can continue to support the life on its surface. So, in all of our travels through the universe, from Earth all the way out to the cosmic microwave background, we find that there is literally no place like home. And with that, welcome back home. Welcome home to planet Earth, and we hope you enjoyed our tour of the universe. Thank you all very much.